Uh, this is a sample test for 2 degree of freedom system, a question on 2 degree of freedom system. So this is from special semester 2019-2020. So let us see how do we solve a 2 degree of freedom system. So in the first question, so you can see we have this motorcycle frame model as a rigid body with 2 degree of freedom system. And they gave you that the frame has mass of m, and the length is an additional of L2 and L1. Okay, so you can see that there is a center of gravity G, and you also have K1 and K2, and from G you have this length. So you can see that it is kind of like a form of a rotational bar problem, okay, where your center of gravity is at the center. Things to note when you read the question, you have to look at which way is positive. Normally it's stated in the center. So the center in the question, yeah, the center is G. You have L1, okay, horizontal distance L1 and L2. So the moment of inertia about axis is J. So you have these two stiffnesses. The motion of the system can be described by generalized coordinates xt. So the two coordinates x and theta. So that is also how you know that it is a 2 degree of freedom system, when you actually have two coordinates describing the motion. So xt is vertical downwards, and theta t positive is basically clockwise. Okay, so xt goes down positive and theta clockwise is positive. So you want to use Lagrange method to get the EOM. Okay, and then the second part, you want to get the characteristic equation, natural frequencies and mode shapes given the parameters. Okay, it's this kind of question is very common, where you are actually just solving 2 degree of freedom system, and you are given certain parameters to solve for characteristic equations, natural frequencies and mode shapes. So all of the 2 degree of freedom questions are very similar to this type of question. It's just whether you are asked to use Lagrange or Newton's second law. And for this one is the rotational bar problem. So let us go ahead and solve this problem. Okay, so I've drawn the figure here, so you can see that I've drawn that x going down, okay, to remind myself is positive, and clockwise is positive. So in this system, normally, because 2 degree of freedom system do have relative displacement, so before you actually can write use Lagrange equation, you actually need to determine the relative displacement for K1 and K2. Yeah, so this is the first thing that you need to do. So the easiest way is normally to assume a positive x for both K1 and K2. Okay, what it means by that is basically, if you actually see here, okay, as I already draw, okay, there are two main steps basically. You need to draw, okay, draw arrowheads for K1 and K2 downwards, okay, because we already defined in the questions downwards is positive. So you can see here, okay, the red arrowheads for K1 K2 are downwards to show that it's positive. Same direction as this assumed direction for your x. Okay, the second step is actually you have to determine whether your L theta, okay, either L1 or L2, okay, is positive or negative. So in this case, the question already defined, clockwise is positive, counterclockwise is negative. So based on the same arrowhead, So if you go from, let me just change the color to pink, you can see that this is the pink highlight actually shows the point of rotational point. So if from the point to this arrowhead, you can see, okay, so it's counterclockwise. Okay, that means your L1 theta is negative. Okay, whereas for this arrowhead K2, from the pivot point to this arrowhead, all right, so it's clockwise. So I can write that as clockwise. So here the length is L2, so if it's clockwise, it's positive L2 theta. All right, how do I get L1 theta and L2 theta? If you actually remember, basically if I draw a small triangle from this point G here, so it looks like this, yeah. So this is your X, this is your theta, and this is your L1. So actually your X for the rotational part is equals to L1 theta. Okay, whereas this side here, this X for K2, if I call this X1, this is X2. So this X2 in terms of theta is basically L2 theta. Okay, so that's how we get the expression L1 theta and L2 theta by using the concept of the small triangle. All right, so we've done with steps 1 and step 2, where you can actually see that one side must be negative. So in this case, this side is the left hand side, so you get a negative there. All right, so once you get that, you can clearly write. So maybe I just remove the point here. You can actually you can even draw the action reaction forces if you want, and you can actually write the forces here, which is K1. Your X is already positive, yeah, so K1X minus L1 theta, whereas here the force is K2. You're using the same X plus L2 theta. Okay, that's how you write the forces. So once you have the forces, then only you can use Lagrange. So you have all the forces defined. So now in Lagrange, you just need to identify the kinetic energy, potential energy, and also the release dissipation function. However, here you can see for your kinetic energy, you do have your mass and your J, so you just identify elements. So the mass equation would be in this form. Okay, have mx dot square plus, so this equation you need to memorize is just the energy equation, yeah. You just have m and j, so that's why you have these two terms, and then you do not have any damper, so no dissipation function, so easy peasy. And then after mass and j, you only have springs, so you have k1 and k2. So this is where you make use of your relative displacement equation for the k just now. So you have k1, so instead of just x square, you have x minus L1 theta, okay, square, plus half k2 x plus L2 theta, so everything squared. Okay, so basically you are using these two equations here to define your potential energy that comes from the springs. And you also do not have any Q. Okay, so if you look at these generalized equations, this Q here is actually input to the system. So in our case, sorry, it's not theta, yeah, the Q is 0. So you only have kinetic energy and the potential energy. So you can expect that these two terms, these two terms will become 0. So normally in Lagrange, when you have 2 degree of freedom system, it's so easy if you do a table like this. All right. And I've divided into 2 sides here. The left hand side is for your x and the right hand side is for your theta. Okay. So we have these 2 tables here where you can actually write because the q, okay, this q in the Lagrange represents each coordinate. So in this case it's x and theta. So I've arranged all the equations. You can see there are here I divided into 1, 2, 3, 4, 5 terms. So that's why I have all these 5, both with respect to your x. Okay, you can see here all x, and the other one with respect to theta. So it's actually these terms comes from the Lagrange equation. Okay, from this equation here. So how do you actually do this? Is you referring to the terms here. If for the first term dt x dot, so you can see the equation for your kinetic energy here. You do have your x dot. So when you actually differentiate that, you only look at these expressions. Yeah. So if you take the derivative, because your theta dot becomes constant. So you only take a look at your x dot term, and if you differentiate that, what you have is 2 times half is 1. So that's why you have mx dot. That's all. Okay. Do the same thing using the same equation. Okay. But now, all right. But now you are actually just focusing on your theta dot with respect to theta dot, which is this expression, because now your x dot is actually your constant. Okay, because you are differentiating with respect to x dot. So 2 times 1/2, which is 1, so it's just j theta dot. Okay. Then you have to differentiate it with respect to time, the second term with respect to time. That means instead of just one dot, okay, you have another dot. So it's easy peasy. The second part is just you add another dot. Okay, because x dot means dx dt. So when you actually differentiate with respect to t, you just put another dot. So same as this one, so you would have j theta double dot. Okay. Then next, you look at the dt dx. Okay, you're still looking at this equation, but you cannot see there is no. If you see from this equation, there is no x term or even theta term. Yeah, so that's why for this expression, the answer is 0. You only have x dot and also theta dot, but you do not have x and also theta. You don't have that. So that's why this expression is normally 0. Then you go ahead, the dd are also 0. As I mentioned, there's no damper, but the next equation is the dv. So dv is referring to this equation here. So for dv dx, so you are referring to this equation for the v, so with respect to x. Okay, so for if with respect to x, that means both terms is going to be there. So the first term, then it's going to be 2 times half, so you have to write the whole term, which is k1 x minus L1 theta, and then the power of 2 will become power of 1, and then you have another term, and then you have to differentiate x, but x is 1, so you just have to times 1, Then you go for another term is your K2. So your K2, same. The 2 times half, you get 1. So x plus L2 theta. Okay, so the power of 2 will become 1. And your differentiating x is 1. So you don't have to do anything. So it's just that whole expressions. But now, if it's with respect to theta, so then you have to differentiate your negative L1 theta. Okay, that's why in the second part, you still have K1x minus L1 theta to the power of 1, but then you have to differentiate this term. Okay, so that's why you have to times negative L1. Okay, do the same thing for your K2 plus K2. You have x plus L2 theta to the power of 1. Differentiation with respect to theta, you have to times L2. Okay, because you differentiate this expression. Alright, so we've done with all the terms here. And from there, you just add all those terms up. If you do that, you can get your EOM. Okay, just add them up. What you have, your basically this term mx double dot, and also this term, that whole term, same as this one. You have that term and this whole term. Okay, so if you add those terms highlighted in pink, you will actually get the EOM. Okay, so the first one is given by the first this equation, and then you have the j theta double dot equation. So from there you can also check, okay, in the questions whether it's correct or not. You can see that this m times x double dot plus k1x, so you collect the terms for your x here. So in your first equation, you have your, for the x term, you have k1 and k2. And for your theta term, so you can see that for your theta term, okay, you have k1 L1 is a negative, okay, and also you have k2 L2, okay, is a positive. So that's why you get that. And then for the j theta double dot, which is the second equation, so the second equation, you only have j theta double dot. This is 0 because there is no m term there, x term, x double dot term there. And then you look at for the x, okay, look for the x term. So the x term here, the x term represents you have the k2L2 and k1L1 minus, so that's why you have that. And then you look for the theta term as well. So the theta term is positive k1L1 square, okay, which is this term, times negative L1 square. And then you also have this term k2L2 times L2, so you have k2L2 square there for your theta. So that's how you arrange the matrix, and you get the same equation as in the question. Okay, we've done with the part A. So for part B, they give you all the parameters and they want you to compute the system's characteristics equation, natural frequency system mode shapes. So using the same EOM, first of all, you have to write the assumed solutions. Okay, we are assuming all harmonic motions. So here I'm using it as an exponential function. It doesn't matter. You can also use a sine function or cosine function as your assumed solutions. If you're using sine and cosine function, you do the same thing. You get the first you have to compute the second derivative because you have all these terms that you need to substitute, okay, with the solutions. So in this case, I have xt and x double dot. Okay, I'm using exponential function. So it is still the same. Okay, maybe in the notes you can see you can also use a cosine or sine function, as long as it's harmonic motion. So once you have that, so what you need to do, you just substitute into the equation. So you just need to write your x double dot expression. So here you, instead of x double dot, you write negative x omega squared x e to the j omega t, and this also you have your negative omega squared theta e j omega t. Okay, so then you will need to do the rest. So you have these expressions. When you substitute, okay, you can actually factor out the ej omega t to the right hand side. Okay, so you can see all this ej omega t, you can bring it to the other side of the equation. That means 0 divided by ej omega t. Okay, so you get 0 as well. So you only left with these expressions. You have basically negative omega square here. You have to times with your m and your j. So that's why you have negative m omega square and negative j omega square. So you can see you have your x and theta both, and you can combine the terms in that case. So you can combine and substitute the values. In this case, you can see that you have negative m omega square and k1 plus k2, where you have to times your x here. Okay, so you see that your k1 plus k2 is 250,000. So you have that 250,000 minus your m omega square, which is 140 omega square, and then you have 0. I'm looking at the first row here, and then you have 0. Okay, and then you have k2l2 minus k2l1. So if you actually calculate that with your l1 and l2 value, if you calculate that, you get 700. Okay, same as for the second row, k2l2 minus k1l1, and then your k1l1 square, you get 10430 minus 25. So you may want to check that out, how we just substitute those values here. So negative 25 is basically your j value, yeah, omega square. Alright, so after we combine both terms, so everything is in terms of capital X and capital theta now. Okay, you can actually apply. So if you remember the steps, once you get it in this form, you can actually get the characteristics equations where you apply the determinant. Okay. Okay, determinant means you basically times cross, yeah. So if I call this one A, B, C, D, so determinant is AD minus BC. Okay, so you have to times here, and then you minus with this. Okay, if you do that, then you should get these whole expressions. Maybe I made it okay. This 2 is 25, not 250. Sorry, yeah. Let me just erase that. So this one is 25,000. So you have 25,000. 25,000 minus 140 omega square, and then you have 10430 minus 25 omega square minus you have 700 square equals to 0. So this is the first part of the solutions, which they ask you to get the characteristic equation. Alright, 6O equals to 0. So this is the characteristic equation. Then to get the mode shapes, you have to find, so this one is the, once you get the characteristic equation, you can use the quadratic formula, or you can also use your calculator. If you use your calculator, so your A, using the quadratic formula inside your calculator, so A is equals to 1, your B is 595.77, and your C is 74360. Yeah. So once you put in your calculator, don't forget, because this is to the power of 4, you need to take the square root of the answer. So same as the second answer. So there will be two answers. The smallest answer will be the first natural frequency. The second, the higher value will be the second natural frequency. So don't make a mistake with that. So you can see that you have to take the square root of those answers. Yeah, then only you get it in terms of omega 1, omega 2. Else your answers are in omega 1 square. Okay, answers are in omega 1 square. So after you take the square root, you get omega 1, omega 2. Then you can substitute into the equation. So which equation do you use to substitute your omega 1, omega 2? If you remember, we have this equation. You just look at the first row of this equation. Yeah, you just look at the first row of this equation. That will be the equation for you to substitute your omega. So based on that equation, basically when you want to substitute you have to assume your one value of x equals to 1, and you want to solve for your theta. So if you write that equation, basically that equation is 25,000 minus 140 omega square times x, okay, equals to, so the 700 theta, you can bring it to the other side of the equation. So you want to express it in terms of theta, negative 700 theta. So your theta is equals to this whole expression, which is 25,000 minus 140 omega square divided by negative 700. Okay, and you have your x there. So this is the general equation that you're going to use. Okay, maybe I put a parenthesis, that'd be better. So then you can start substituting. So you have two conditions. The first one is when your omega equals to omega 1. Okay, so for the first mode, if you substitute in here your omega value, then you will get, for the first mode shape, you will get negative 0.123. Do the same thing for the second natural frequency. You substitute your omega term in terms of 20.44. So x remain the same as 1. So you will get 47.84. So the way to write your mode shape, okay, so the first mode shape, since your x is 1, so your theta is negative 0.123, because the way you're writing is x and theta. Okay, so same as this one, the second mode shape will be 147.84. So that one represents x, and the bottom value represents theta. So that's how you write your mode shapes. Alright, so I guess that's all for this problem. So this will be the final answer for the mode shapes. Okay, we've done with the characteristics equations and the mode shapes. natural frequencies and mode shifts. So I hope you can remember the steps in order to get these three main parameters. Alright, thank you.